Okay, welcome to 8.3. We're still talking about binomial distributions and that formula we used in 8.2 Part B. But you're going to find the formulas of this section to be much simpler than the binomial distribution formula we used in the previous section. So that's one little sigh of relief you can take. This actually is a little bit simpler, and it's a pretty easy concept that you should be able to get through really quickly. First, let's talk about what this means. What does it mean to find the mean of a binomial distribution? So remember that the binomial distribution uses the idea of the random variable x, where x is counting the number of successes in n different trials or experiments. And so when we talk about the mean, what we're talking about is we continue to repeat this experiment over and over again. What is going to be the average number or the average count of successes every time we repeat it a certain number of times? And if we look at a basketball player and how many times they can, in history, make a free throw. For example, if we have a basketball player and he's making 80% of his free throws, in other words, his historical average is about 80%. If he was to throw 10 free throws, how many of those 10 would we expect to see as far as successes, meaning the ball makes it into the basket? And the way we find it, well, we take 80% of 10, which is 8. So we multiply 0.8, the probability of success, by the number of trials. Right there, that is the mean of the binomial distribution. In other words, we're saying that in 10 trials with an 80% probability of success, we'd expect to see, on average, 8 successful throws, meaning they make the basket, every time. The formula for mean of a binomial distribution is the number of trials multiplied by the probability of success, p. All right, example number 2, the number x of CDs that are defective has an approximate binomial distribution with n equal to 10, so we have 10 trials, taking out 10 CDs, and a probability of 10%, meaning that there's a 10% probability that a CD is defective. What is the mean? Well, here we take our number of trials, which is the number of CDs, 10, multiplied by the probability of success, p, which is 10%. So we have 10 times 10%, and the outcome is 1. Therefore, the average number of CDs that will be defective in a batch of 10 is, we would expect to see, on average, 1. I told you that they were simple. So when n is equal to 35 then, so let's say we're picking out 35 CDs, what would be the mean of that distribution? Well, again, 35 multiplied by 10% is 3.5. But of course, we can't have a half of a defective CD. Either it's defective or non-defective. But what that tells us is that on average, we're going to expect to see between 3 and 4 defective CDs out of every 35. All right, what about standard deviation? What about the average deviation of the data going from trial to trial to trial? This is also directly related to the size of the sample and the probability of success. In fact, we use N and P again, but then we also throw in the multiplication by the probability of failure. N times the probability of success times 1 minus P, which would be our probability of failure. We take that number and we find the square root of it. So, going back to our previous example, with a sample of 10, probability of success of 10%, what would be the standard deviation? And plugging these in, we get 10 times 0.1 times 1 minus this should be 0.1, not 90. So the result of this actually is 90. That's my probability of success. We got a little typo there. And we can see that here. 10 times 0.1 is 1, and 1 times 0.9 is 0.9. We take the square root of 0.9. We get 0.9487. Obviously, again, it's a decimal value, so we kind of think of it really close to 1. We say that the individual trials will deviate from that mean amount of 1 by about 1 CD. So, in other words, 68% of the time, when going back to the empirical rule, we could expect, since my mean is 1, that it'll deviate 1 standard deviation to the left to the right. So sometimes we will see 0, and then other times we may see 2 of those. But that's going to deviate around 1 by about 1 CD on average. So it's just giving us an idea of over time what we could expect to see with our number of successes. If we go back to our n equal to 35, again, plugging all this in, we see 1.775. Therefore, the number of successes from trial to trial will deviate from 3.5 by an average of 1.775 defective CDs. We can interpret that 1.775 as between 1 and 2 is our deviation, leaning toward 2 because it's a lot closer to 2 than it is to 1. Remember that these very simplified formulas we can only be used in binomial distribution settings, where, remember the caveats we had for binomial distribution. We have to have a fixed number of trials. Each trial is independent. There's only 2 possible outcomes. One may deem a success, and hence the other becomes a failure. We label the success as P, and then 1 minus P is my probability of failure, and the random variable X is the number of successes with n trials. This concludes this lesson on the mean and standard deviation of the binomial distribution.